Okay, now continue. So given the 25 years of the neutrino oscillations discovery, we are now with Alexei Smirnov. That needs no introduction whatsoever. So it's quite a pleasure to meet Alexei. I would say that besides a great scientist that everybody knows, I would say that from personally speaking, because I was sitting close to him for a couple of years at Max Planck, he's an excellent person, really welcoming, and I advise everybody to get to know this man. I was really a pleasure to get to know you, Alexei, from the bottom of my heart. So thank you so much for accepting to talk to me and about the neutrino. And I already asked those Alexei which questions I would ask him, so he have an idea what's going on. So the first question I ask is, why should we care about neutrino oscillations? Alexei, please, could you elaborate on why should we care? Why the hydrogen physics community should care about the neutrino oscillations?
Well, thank you very much, Farinaldo, that you invited me to to talk about these things. And so I'm actually honored that to some extent I should give some view of what's going in the field. So neutrino oscillations discovered first in atmospheric neutrinos. First of all, this is a very beautiful phenomena. And this is the phenomena which has many various aspects. So this is phenomena, this is quantum mechanics at macroscopic scales, first of all. This is why it is so much interesting. Well, it is very rich phenomena because we have different neutrino species, and different neutrino species oscillate somehow in different way. We have different energies, huge energy range we have studied. So there are different sources of neutrinos, different environment in which oscillations occur, and of course, environment affects neutrino oscillations. We have propagation of neutrino in space and time, and therefore we are to some extent testing properties of the space and time. And even more, so this is quantum mechanical phenomena, but people start to discuss how oscillations looks like if we change somehow quantum mechanics. So in this sense, oscillations check even basics of quantum mechanics, if you want. So this is kind of aspect of neutrino oscillations themselves. Well, I should say that some of these aspects have not yet been elaborated completely. And for instance, oscillations in neutrino media, where we have neutrino-neutrino interactions, and therefore oscillations in nonlinear regime, so to say. Now, what are implications? So what is kind of the meaning of this discovery for particle physics? So first, what are implications? So first of all, it's what we are saying that neutrino oscillations are due to neutrino mass and mixing. So that discovery of neutrino oscillations means a discovery of neutrino mass. And you see, even here we are kind of facing some open questions. And the question is, what do we mean by the mass itself in the first place? So it seems that neutrino mass is not the same, or not exactly the same, as masses of other fermions in the standard model. So it may be seesaw mechanism, for instance, but it may be something else. Actually, what oscillations are telling us that in the Hamiltonian of propagation, so the theory of propagation of neutrino, there is some term which is proportional to the mass squared over the energy of neutrino. Not even mass, so we are not probing directly the mass of neutrino in oscillations, but mass squared. And there's a big difference actually in this. So everything which has a kind of feature 1 over the energy, or something, some parameter over the energy, can reproduce the neutrino data. And So it's still open question, what is the nature of neutrino mass? Is this a vacuum mass, which is produced by vacuum expectation value of some field, or maybe this is something which is produced by expectation value of the field, not vacuum, but expectation value, which means that we have system of particles and scattering of neutrinos on the system of particles, on dark matter, on very light dark matter, and it shows up completely as just a usual mass. So this so-called effective or refractive mass has some unusual properties. For instance, it depends on energy. It depends on time, in some cases. It depends on space point. So that in the center of the galaxy, we have bigger mass of neutrino than near the sun. So oscillations actually not only establish that there is something like the mass, and in fact, the mass is the simplest explanation of oscillation data, but also oscillations can probe the nature of neutrino mass. Not Majorana and Dirac, this we are not testing in neutrinos, but the nature in a sense of what is the origin of the neutrino mass and how it is generated. And now it's kind of interesting topic and people are studying how to test this. And to test this, we need to, for instance, measure neutrino parameters in oscillations at different energies. It probably we may observe some difference at very high energies and low energies. Or we may probably see that a neutrino mass is bigger in the center of galaxy. Of course, this we can probably test using supernova neutrinos. So for this, we need to detect. Now, large mixing, which is observed in oscillations of neutrinos, this is puzzling. I remember when we in 90s discussed neutrino oscillations, it was kind of idea that maybe neutrinos will help us to understand what's going in quark sector. And if there is a unification of quarks and leptons, if there is a grand unification, but the situation now, it is even more puzzling. Now we are struggling to accommodate small mixing in quark sector and large mixing in leptonic sector. And a whole bunch of the ideas related to this and developments related to attempt to explain difference of the mixing in quark and lepton sector. So, and of course, the smallness of neutrino mass is also an explanation, is another direction of development. So smallness of neutrino mass probably is associated to existence of some very high mass scale or energy scale. On the other hand, it may happen that neutrino mass is associated completely with different physics or some very low energy physics, say dark matter or dark sector at very low energy scales. And still, this is the open question, and I think we need to address this question in future and try to test and to find a way to check what is the nature of neutrino mass and how it is organized. Surprisingly, that still we don't know, we have no answer to this question. So essentially, we are at the level when it was said that neutrino oscillations are discovered and neutrino mass is behind this and behind these oscillations. Now, of course, another aspect is application, right? We can talk about applications of neutrino oscillations. And with neutrino oscillations, we can probe the properties of space-time. We can probe the properties of medium. We can perform tomography of the Earth, and also tomography of the stars, for instance. If a shock wave propagates inside the supernova, using oscillation data, we can trace how this shock wave propagates inside the supernova. And neutrino oscillations is a must to take into account in analysis of various data. We know that, for instance, in high energy cosmic rays, we explain flavor equilibration. So we need, of course, take into account oscillations in the case of solar neutrinos, supernova, nuclear synthesis, etc. So this is my answer to your first question. This is what actually oscillations mean, at least for me.
Okay, thank you so much. And I guess one of the things you already mentioned sort of somehow related to the second question, which I guess you can kind of gave us an idea of what you think of the future, which is, in your point of view, what do you think there are the relevant open questions and how we can even promote, let's say, broader, which direction the neutrino physics community is headed in the way you see, which questions which are really relevant for the foreseeable future? So, I mean, what are the main topics that we should focus on?
Well, let me tell you that, of course, many things already discussed, and I'm not sure that I can add much to what has already been clarified and what is in the programs of the studies. The only new things which I believe one needs to also to think about is this nature of neutrino mass, again, in a sense, what is behind usual vacuum mass, some seesaw type mechanism, which is actually a seesaw mechanism. Already in this mechanism, not only a single wave of Higgs field participates, but we have at least square of Higgs field, and probably some other waves are involved which produce masses of right-handed neutrino. So I think it's not appreciated much that in fact neutrino mass or masses, they are dynamical characteristics. It's not like just something, some parameter which is fixed. And even in the standard model, you know, in the standard model, neutrino mass depends on a wave, which actually can change in different space-time points also, for instance, in the presence of topological defects. And neutrino mass can be generated not by just our Higgs wave, but by something else, like a Higgs triplet, for instance. Even coupling constants, as we understand, are dynamical parameters. It's not just constants. Right. Not only renormalization group effect is involved, but also coupling constants, probably the functions of some other fields, of flavons or moduli fields, which means that they are dynamical characteristics. So they are transformed under some symmetry transformation, etc. So the question is that we need probably to kind of undertake some efforts to, and probably formulate the program to really to convince what is really this mass, which produce neutrino oscillations. You know, from the beginning, something strange is with neutrinos due to the smallness of neutrino mass. So most probably it's not exactly the same as the masses of electron and muon and quarks, something else. But the question is what else? This is one point. Taking point of view that neutrino mass has origins from some high energy physics, which is probably the most plausible situation and maybe the simplest one. So that this is kind of hard mass. It's not changing. It's not much depending on medium, on space-time properties. Then the questions are quite clear. So we still don't know what is the mass hierarchy, which I believe is the question number one. I think many things, further developments depend on this, the answer to this question. Of course, CP violation. Here we may be quite disappointed because it may happen that CP violation phase is small and therefore the effects are quite small and it will be difficult to detect them. Of course, neutrino oscillations is very powerful tool to study some new physics beyond the standard model. And we know that we can study some new neutrino interactions, say, local interactions, and people focused very much on this, but also neutrinos may have new interactions with very light particles and very light mediators. And I think we can also focus on these possibilities and further test if there are couplings of neutrinos with this very light dark sector. So this is new trend, and I think still many things can be done in this direction. Now, concerning the theory of neutrinos themselves, here we actually have subtle aspects related, for instance, with entanglement, related to decoherence, and surprisingly, after so many times, people now very actively discuss these subtle issues. Dependence of or entanglement of neutrinos with particles produced together with neutrinos and also with medium. So now with very high accuracy of present-day experiments, we can actually seriously address these questions. I think this is very important and interesting areas. Now, I didn't mention about sterile neutrinos. Again, I believe this is extremely important to put strong bounds on the mixing of active and sterile neutrinos. I'm not sure that we have really very kind of reliable evidence for these sterile neutrinos. But if they exist and they mix with usual active neutrinos, then that may change completely the picture we are constructing to explain neutrino masses and mixing and properties. Even large mixing in leptonic sector can be due to mixing with sterile neutrinos. So I believe that one needs to exclude this mixing of sterile neutrinos up to level, say, sine squared to 10 to the minus 3 or even better. So then we can say, okay, sterile neutrinos are just, if exist, a small perturbation of the picture with usual 3 neutrinos. Now I think very important information and very important input comes from cosmology and neutrino cosmology. And so, you know, fortunately soon Euclid will produce something for us, and we may actually understand something more about neutrinos. Mixing interactions of neutrinos with dark sector. Again, I'm coming back to the same issue, and that can be tested having more detailed information about structure formation. So interesting aspect, for instance, possible existence of complex neutrino states or neutrino stars or some kind of formation of neutrino structures in the universe. Still open question, what is really neutrino structure of the universe? So another aspect, of course, very important is detection of high energy neutrinos, ice cubes. So that's certainly extremely perspective area, and I believe we may learn a lot from this in future. Then relic neutrinos, I mean, low energy, so on the other hand, on the other side of this energy axis. And yeah, so maybe this is a very long perspective and maybe some generic, but this is something which one should think about. And actually, tests of these relic neutrinos, if they have coupling, say, with dark matter, can be probably easier than the direct detection of relic neutrinos. And of course, neutrinos and gravitational waves aspects. So the simplest connection, of course, that gravitational waves modify space-time, right? So you have, and therefore that can affect also neutrino oscillations. So what else? Then I said already that still open question about supernova neutrinos and collective oscillations in the central part. So every day almost there are some new papers and new ideas. And we need really to understand what happens in very inner part of collapsing star. Otherwise, we will not be able to give an interpretation of what we will observe. This is very complicated issue, although maybe solution will be very simple. People just like in the paper today, for instance, show that it will be flavor equilibration. That's it, which is very kind of sad, because then there is no effects of neutrino oscillations further. We just have this flavor equilibration, maybe not sensitive to anything after central parts of the star. Concerning the theory of neutrino mass and mixing, so clearly that attempts will be continued. So now we have this phase related to so-called modular symmetries. And there are some nice ideas, but I'm not sure that we will come to final conclusion at this level. Things are more very complicated, it seems, and we have no very simple relations which can be then explained by very simple basic principle. So it may happen that Weinberg is right, and so we have just this dimension 5 operator and nothing more. And in this way, actually, mechanisms of neutrino mass generation will affect the rest of the standard model in very minor way. And so then that's it. Actually, that's it, man. as far as the theory of neutrino mass is concerned. I didn't mention experiments, of course. That's a right. Story, and this is different story. So this is more or less what I wanted to say.
I'm satisfied though. I really liked. So I think let me just add something that I'd like to have your opinion about it. Alexei, is that for instance, a few years ago we are still like thinking about the idea of probing neutrino interactions with light species using accelerators, such as people when Dune came, so maybe SND or Dune, we could probe light species interaction with neutrinos. And now we have these recent measurement by the SND at the LHC, which really observed these neutrinos from muons and interacts with protons at LHC, has published in PRL, I believe. So you think that's like, I mean, is now an era where we can really probe physics beyond the standard model using neutrino scattering of some sorts? I mean, it's not because before we had neutrinos oscillations and cosmology and neutrino level beta decay. So we're like basically the end theory of neutrinos, model building of neutrinos oscillations, just observation of neutrinos oscillations, and cosmology and neutrino level beta decay. Basically, were these like 4 pillars of neutrino physics. And now we are reaching an era. Now we can really probe neutrino scattering of particles. And do you think that we can really have a big advancement in the field probing those interactions using neutrino scattering?
Well, first of all, I have discussed oscillations, not interactions, and I kind of focused in my talk on oscillations. This is, of course, a very big area of research and interesting ideas, of course. And I haven't discussed these discoveries of new physics in interactions. The answer is yes, of course, this is interesting stuff. And we can discuss some new neutral leptons, for instance, with the mass, I don't know, 100 MeVs or things like this, using high energy neutrino beams, or GeV range, like, say, if you think about new MSM model, and people are also in future will probably try to search for these GeV scale neutrinos, heavy leptons, etc. Yes, of course, this is important area, and yeah, so one can expect important results. Sure. This is another talk, you know.
Okay, all right. Okay, Alexei, that's all I had to ask you. I'd like to thank you all who listened to us for all this time. So thank you so much for your attention, and I'm just gonna now end the meeting so I can talk with Alexei with no more obligation. But thank you so much, Alexei, for your time. and it was really a pleasure to hear your words about it. So you are an expert in the field, and a well-known expert in the field, and having your thoughts, I think, is really important for us to see how the future should be, because you have very large experience, and you are a well-known researcher, and as you see, you've seen online live, right? So he read a paper from an archive today. So that's the kind of guy we're talking about. So he's up to date with everything that's going on in physics research. Let me just give you a story, Alexei, that I think I never told you. So shortly after I arrived at NPI, and there was a paper that came out about dark matter neutrinos something. I don't remember what was the paper about. I think it was the dark MSW effect, that we eventually invited someone to give you a talk at NPI. The paper came out, let's say, 2 days morning. I arrived at NPI maybe at 10 a.m. or so. And then he was, hey, Fernando, did you see the paper today? I said, man, my goodness. This guy already saw the archive today, this morning. I said, that's Alexei, okay? So just to give you an idea that this guy is up to date with everything that's going on related to neutrino physics. So that really impressed me. So there wasn't one, I think it was maybe my second week at NPI. I was, wow, this guy is really aware of everything that's going on in his field. So it's just a line to say that how much you're involved in this research and how important you are to the high-energy physics community. Thank you so much.
Thank you very much, Farinaldo. Thank you.
Bye.
Bye.